Okay, hello everyone. Welcome to day 2 of AKBC. It's my great pleasure to introduce our first speaker today, Jia Deng. Jia is an assistant professor of computer science and my colleague at Princeton University. He received his PhD also from Princeton University and his bachelor degree from Tsinghua University. So Jia is very famous for his lots of pioneering work in computer vision. In particular, he is the creator of the ImageNet project. So Jia has won numerous awards, including 2 ECCV Best Paper Awards, an ICCV Mark Prize, a Sloan Fellowship, an SF Career Award, and a few others. Today he is going to tell us something very different, and the talk will be about his recent research on learning symbolic rules for reasoning and automated theorem proving, which is actually very close to our AKBC community. So without further ado, Jia, please take it away.
Thank you, Danchi, for the very nice introduction. I just want to check if you can hear me okay.
Yeah, good.
Okay, then let's get started. Hello, everyone. Today, I'd like to present our work titled Learning Symbolic Rules for Reasoning. This is joint work with my PhD student, Kai-Yu Yang. In this work, we address the problem of reasoning in natural language. Let's say we have a set of assumptions. The elephant is big, the elephant is tall, big, tall things are strong, and if something is strong, then it likes cats. Humans can easily deduce from this set of assumptions that the elephant likes cats. This kind of reasoning is an important part of human intelligence and has been the subject of research dating back to the beginning of AI. So how do we approach this task? One existing approach is to perform semantic parsing to convert the natural language into formal logic, such as first-order logic consisting of predefined predicates. Given the logical formulas, we can use a theorem prover to generate the conclusion. The advantage of this approach is that the theorem prover performs explicit symbol manipulation. Particularly, it produces not only an answer, but also a proof that demonstrates how the conclusion is arrived at following inference rules. The proof is interpretable, and its correctness can be mechanically verified. On the other hand, a disadvantage of this approach is that it relies on a predefined ontology. That is, we need a formal language consisting of predefined terms, functions, and predicates that represent the meaning of natural language. Such an ontology is generally difficult to construct, especially if we want to cover a wide range of concepts in natural language. Another category of methods uses neural networks to perform soft reasoning without explicitly manipulating symbols. For example, we can just train a neural network to map the input to output. Specifically, we can train a transformer to map the assumptions to the conclusion. This approach is simple and flexible, without the need of an ontology and a semantic parser, and it can achieve good performance on many benchmarks. However, it can require a large amount of training data and can generalize poorly to out-of-distribution examples. And more importantly, the neural network is a black box, which is hard to interpret and verify, making it undesirable in certain applications critical to safety and security. Here, I'd like to share some of recent work toward developing a symbolic reasoning system that can potentially overcome the limitations of prior work. We'd like it to be rule-based in the sense that it performs explicit symbol manipulation using explicit rules like a theorem prover. We'd also like it to be interpretable and verifiable. That is, it should produce not only answers, but also proofs that are mechanically checkable. Third, we'd like the system to be able to directly work with natural language in the sense that we do not need to construct an ontology, nor do we need to rely on a semantic parser to map natural language into formal language. Lastly, we'd like the rules to be learned from data as opposed to constructed by hand. This last point is crucial because manual construction of rules can be difficult to scale. Our approach consists of two parts, meta-QNL and meta-induce. Meta-QNL is a rule-based symbolic system that specifies what it means to reason symbolically. Meta-induce is an algorithm for learning rules from data. Let's start with meta-QNL. Meta-QNL is a symbolic system. In meta-QNL, a system is a sequence of words and variables, such as the elephant is X, where X is a variable. They also include ordinary English sentences without variables, such as the elephant is tall. We call our system a quasi-natural language because it has a formal syntax, but is compatible with natural language. A rule consists of multiple sentences as its premises and one sentence as the conclusion. For example, this rule has two premises. It tells us that given the elephant is X, and if something is X, then it's Y, we can derive the elephant Y. Rules with variables capture abstract knowledge that is independent of specific instances. We can think of variables as placeholders that are universally quantified. When applying the rule in reasoning, they are substituted with concrete sentences, that is, sentences without any variables. Let's look at an example. Here we are given two rules, and we have four assumptions and a goal we need to prove. In reasoning, we apply the rules to generate a proof. So we also call this process theorem proving. Starting from the assumptions, we choose which rule to apply and how to substitute the variables. First, we can apply the rule on the left. Here we can pay attention to the color to see how variables A, X, Y, and Z bind to concrete sentences. Applying this rule gives us a new sentence, the elephant is strong. Then we apply the second rule, which is the rule on the right. After applying the second rule, the goal is reached, and we have a proof that is interpretable and verifiable. This is how reasoning works in meta-QNL at high level. Meta-QNL is inspired by and resembles MetaMath, which is a computer language for mathematical proofs and uses substitution as the sole inference procedure. Meta-QNL can be thought of as an extension of MetaMath to natural language. To perform reasoning in meta-QNL, we need a knowledge base of rules. How do we obtain such a knowledge base? The second part of our approach is a general algorithm for learning rules from data. Given a training set consisting of provable examples and unprovable examples, meta-induce seeks to induce a set of rules that are consistent with these training examples. Each training example consists of a set of assumptions and a goal. For a provable example, its goal should be provable from the assumptions. In an unprovable example, its goal should not be provable from the assumptions. The provable examples can be understood as positive examples that demonstrate valid reasoning. The unprovable examples can be understood as negative examples that demonstrate invalid reasoning. A set of rules is consistent with the provable example if it makes the goal provable from the assumptions. Similarly, it is consistent with an unprovable example if it does not make the goal provable from the assumptions. Ideally, we'd like to have rules that are consistent with as many examples as possible. However, simply maximizing the number of consistent examples can lead to a trivial solution, where we simply create a rule for each provable example, and each rule is just a verbatim copy of the provable example. Obviously, this trivial solution may be undesirable because it may not generalize. That is, it may not be able to prove anything beyond the training examples. Thus, we need to introduce additional terms into our training objective. If we think of the set of rules as a machine learning model, we need to penalize the model complexity. Here, we can measure model complexity as the number of rules. That is, we prefer a small number of rules. And the lambdas are hyperparameters controlling the trade-off between model complexity and its consistency with training data. Now, having defined our learning objective, we need an optimization algorithm to find a solution that optimizes this objective. Meta-induce is our algorithm for finding the rules to optimize this learning objective. We start with a set of training examples. For simplicity, let's assume that we only have two provable examples and no unprovable examples. Each example consists of a set of assumptions and a goal. The first step of meta-induce is rule proposal, where for each provable example, we propose a set of candidate rules that may be useful for proving this example. Note that these candidate rules can be a very large set of possible rules, and many of them can be unnecessary or wrong. In addition, these candidate rules are specific rules with no variables. How to propose the candidate rules can involve domain-specific heuristics. This allows one to design the rule proposer to incorporate domain-specific knowledge. At a minimum, the candidate rules can always include the trivial rules, which are just verbatim copies of the provable examples. These trivial rules guarantee that we'll always have a solution that can prove every provable example. On the other hand, this trivial solution can have too many rules and may not generalize. So we need more steps to make them more compact and generalizable. Given the candidate rules, the next step is to use these rules to try to prove each example. Here, we use an off-the-shelf theorem prover, which tries to find as many different proofs as possible for each example within a given time limit. Here, we see that each training example can be proved in more than one way. Now, given all the proofs discovered, we can collect all the candidate rules that are actually used in the proofs. That is, we throw away unused rules. This gives us a smaller set of rules. Even though we now have fewer rules, the rules are still specific rules without any variables. This means that they can only be used to prove a particular example and lack the ability to generalize. So our next step is rule abstraction, where we try to detect patterns in the specific rules and create abstract rules. For example, here we observe that Rule 5 and Rule 7 can be abstracted into a single rule with variables. We try to discover as many such abstract rules as possible. Here, let's say after this rule abstraction step, we have added 2 new rules, both of which have variables. Now, given all the specific rules and abstract rules, our next step is rule pruning. Here we try to select a minimal set of rules that can prove all the provable examples. This is formulated as a discrete optimization problem, and we'll describe the details in a moment. With the pruned rules, we could stop here. However, we can also repeat the whole process by adding the pruned rules to the candidate rules and run the theorem prover again. This is because we now have the abstract rules with variables. The theorem prover may now be able to discover new proofs that were not discovered in the first round. This can allow us to get an even smaller set of rules. Now, let's go into some details about the rule abstraction step. Here we start with a pair of existing rules, and we want to see if we can create a new rule with variables such that we can generalize both existing rules. For example, this is a new rule that abstracts both existing rules, Rules 5 and Rule 7. In this new rule, we have introduced variables, and we can verify that each existing rule can be substituted from this abstract rule. It's worth noting that there can exist multiple abstract rules that generalize the specific rules. For example, we can abstract Rule A further to Rule B. In addition, we can create Rule C, which is a different abstraction of Rule 5 and Rule 7. In fact, all the possible abstract rules form a partial ordering, from the most abstract to the most specific. Here, Rule A is more specific than Rule B, but A and C are not ordered. Rule A is not more specific than Rule C, nor is Rule C more specific than Rule A. Among all possible abstractions, we would like to pick the most specific ones. This is to avoid overgeneralization of rules, especially when we do not have enough unprovable or negative examples. In this example, this means that we pick Rule A and Rule C, but exclude Rule B. Finding all possible such abstractions is also called anti-unification, which is a well-studied problem in inductive logical programming. Here we adapt an existing algorithm developed by Cassia et al. In a nutshell, the algorithm works by systematically and recursively enumerating the possible most specific anti-unifiers. We can apply any unification iteratively. We go over all pairs of rules, add the new abstract rules, and repeat until no new rules can be added. Now let's go into some more details about the rule pruning step. In this step, we hope to minimize the number of rules while remaining consistent with the training examples. We formulate this problem as discrete optimization over binary variables. First, we have one binary variable to represent the selection of each rule, specific or abstract. We also introduce a binary variable for each proof step. Each of these variables represents whether a particular proof step is selected or can be instantiated given the selected rules. Now, we can formulate the optimization objective. First, we would like to select the proof steps such that each example has at least one complete proof. This means that for the first example, we need to select proof step 1, or we need to select at the same time proof step 2, 3, and 5. Similarly, for the second example, we need to select either proof step 6 or proof step 7 and 9 at the same time. This gives us these two Boolean expressions that state our requirements. Next, for the unprovable examples or negative examples, we don't want any complete proof selected. In this example, we do not have any unprovable examples, so there is no constraint here. If a proof step is selected, there must be a corresponding rule that can realize this proof step. For example, if proof step 1 is selected, then rule 1 must be selected, because rule 1 is the only rule that can possibly realize this proof step. Similarly, if proof step 3 is selected, then we need to have either rule 3 or its abstraction rule B, because these are the only two rules that can possibly realize proof step 3. Finally, we want as few rules as possible. This is expressed as negations of the rule selection variables. Now, given this collection of Boolean constraints, we can formulate a max-stat problem where we seek to find an assignment of the variables to satisfy as many constraints as possible. It's worth noting that all constraints are soft, except the ones that require each selected proof step to be realizable by the selected rules. This means that given a training set, we don't have to prove every single example in the training set. Now that we have gone over the details of our approach, it is interesting to look at the big picture and contrast our approach with deep learning. In deep learning, the model consists of a compute graph with weights, whereas in our case, the model consists of a knowledge base of symbolic rules. In deep learning, the model size can be measured as the number of weights, whereas in our case, the model size can be measured as the number of rules. During inference, deep learning evaluates the compute graph, whereas we perform proof search. In deep learning, researchers pre-specify the structure of the compute graph, whereas in our case, we pre-specify the meta rules, that is, definitions of what constitutes permitted rules and permitted inference. During training, deep learning learns continuous weights, whereas we learn discrete symbolic rules. In terms of the learning algorithm, deep learning performs continuous optimization with stochastic gradient descent, whereas we perform discrete optimization with a max-stat solver. Now let's look at some experiments. In our experiments, we first evaluate on learning compositional instructions. The task format is similar to machine translation. For example, in training, we know walk translates to walk, jump translates to jump, and jump twice translates to jump, jump. In testing, we asked how to translate walk twice. Our method achieves 100% testing accuracy on the scanned dataset, and it learns to recover all of the 20 ground truth rules. For example, this is a learned rule that says if A translates to B, then A twice should translate to B. We also evaluate on logical reasoning on the rule taker dataset. The data examples are similar to the elephant example we used throughout this talk. The goal can be either proved, disproved, or neither, so it's a three-way classification task. This is our method compared to a state-of-the-art method called proof writer. Different roles are accuracies for proofs of different depths. We perform competitively in terms of accuracy, but our model is trained only with 8,000 examples, whereas proof writer is trained on 70,000. Also, our model has only 3,000 characters, whereas proof writer has at least 11 billion parameters because it uses a large pre-trained neural network. It's worth noting that our approach is still at an early stage and has many limitations. First of all, our experiments have only been on synthetic data, not real-world natural language. Another limitation is scalability to very large datasets. Meta-induced does not yet scale to millions of training examples, which may be necessary to learn enough rules to handle the complexity of real-world natural language. The current bottleneck is anti-unification, which can be possibly addressed through better methods for generalizing concrete rules to rules with variables. There are also many interesting open questions. One question is how to customize and improve individual components of our meta algorithm for rule learning, including the rule proposer and the theorem prover. Our meta approach is entirely symbolic, but the rule proposer and theorem prover can involve neural components. The rule proposer can use a neural network to generate proposals, and the theorem prover can use a neural network to guide the proof search. Finally, in its current form, MetaQNL does not allow uncertainty, which is necessary for robustness to noisy input and for common sense reasoning, where many statements are not categorical. How to introduce uncertainty to MetaQNL is an open question. One possibility is to associate probabilities with sentences and rules and further define how probabilities propagate through inference. In summary, our goal is to develop a symbolic reasoning system that can work directly with natural language. To that end, we have introduced MetaQNL, a rule-based system compatible with natural language whose sentences have not only words but also variables. We have introduced meta-induce, a meta-algorithm for learning rules from data. In experiments, our models achieve competitive accuracy but are more compact and data efficient. Finally, the work I've just presented was done jointly with Kyrie Yang, who is a PhD student at Princeton. Now, I'd like to end my talk. Thank you for your attention, and I'll be happy to take questions.
Thank you, Jia. Very interesting talk. Yeah, we do have a bunch of questions, so we can take a few in the next few minutes. Okay, so let's look at the first question. So meta-induce looks a lot like inductive logic programming. Can you please summarize how this is different?
Right. So in fact, you know, this algorithm takes many components of it are really borrowed from the research from on inductive logical programming. So here, the main difference is that we want to extend it to natural language because the prior work on inductive logical programming, they usually impose a lot more constraints. They work on formal language. And here we sort of want to just have a minimum set of formal constraints. And we wanted to work directly with natural language. So that's the goal.
Thank you. Okay, so the next question. For the rule learning algorithm, when abstracting rules from candidates, it seems that using pattern matching may have a low recall and extract more abstract rules than needed because of variation of language use. How do you overcome this issue?
Right. So that's that's a very good question. So this is a sort of a component I think worries a lot more research. So because here we actually don't require for the rule proposer, we can sort of have a better rule proposer that can encode some domain knowledge. It can give us certain rules that are more likely to yield good abstract rules. So that's one possibility of dealing with it. But there are certain other possibilities. For example, we can include more better heuristics in the anti-unification algorithm. This can certainly involve some neural components as well. So, for example, embeddings from neural networks, they might sort of provide cues and good hints about what might be effective abstractions.
Thank you. So the next question is, symbolic methods like this one that you described were very popular for a very long time in NLP, but could not really scale to natural language, which is vague, fuzzy, and ambiguous. Do you have any experience showing that how this performs on natural language?
We don't have numbers present here now. We are running experiments on natural language, but we don't have numbers to present at this point. So yes, we're aware that such rule-based systems had a lot of challenges in the past to scale to real-world natural language. And so here, our sort of main hypothesis is that we want to sort of see how far we can go by learning the rules, and whether we can resolve the fuzziness and ambiguity by automatically learning rules. Because we also have neural networks at our disposal, by combining a rule-based system and neural networks, we might go further than prior work. That's sort of our working hypothesis.
Okay, so we have time for one last question. So can you comment on the possible ways to combine these rule learning methods and the distributed representations and the pre-trained language models?
Yeah, so our algorithm is a kind of a meta algorithm, right? So the only requirement we have is that we want the inference part to be rule-based so that we can maintain interpretability and verifiability. But how to perform inference, how to do theorem proving, that can be done through a neural network guided approach. And also in terms of the learning problem, how to induce the rules, it's effectively a very hard search problem in the symbolic space, and certainly there is a lot of opportunities to have neural embeddings that might guide the search for the learning problem as well.
Great, thanks. So we still have lots of interesting questions in Slido. Maybe you can check out. I also encourage everyone to go to the chat with speaker session. So we still have 30 minutes for that. So let's thank Jia and move on to the next talk.
Thank you, everyone.
Hi, David. Okay, so.
Hello, good morning.
So our next speaker is David Sontag. So David is an associate professor in the Department of EECS at MIT. Before joining MIT, David was an assistant professor at NYU from 2011 to 2016, and a postdoc researcher at Microsoft Research New England. So David received his PhD from MIT and also won the Outstanding Doctoral Thesis Award there. So he's also the recipient of Best Paper Awards at EMLP, UAI, and NERVS, and also faculty awards from Google, Facebook, and Adobe. So at MIT, he's leading a research group that aims to transform healthcare through the use of machine learning. Today, he's going to tell us very exciting research on how to build health knowledge bases. So I'm very excited. David, please take it away.
Well, thank you to the organizers for the invitation. And it is exciting to be here. So at MIT, I sit between the Electrical Engineering Computer Science Department and what's called the Institute for Medical Engineering and Science, where everything healthcare related comes together. And my research really is at that intersection. What got me really excited about healthcare about 10 years ago was that there was this trend to increasing adoption of electronic medical records. Going back to 2008, fewer than 10% of hospitals in the United States had electronic medical records, and today that number is well over 90%. Now, what that means is, as a machine learning person, this presents an enormous opportunity both to use that data that was collected to learn about medicine, and that's what we'll be seeing about in today's talk, and then to use that knowledge that we've learned about medicine to improve clinical decision-making and ultimately to help patients improve their healthcare. So there's a real wealth of digital health data that's being collected as part of those electronic medical records. You're probably familiar with imaging data or vital signs, lab tests, but there's also a huge amount of unstructured clinical data in the form of notes that have very rich information about what's happened to a patient in the past and so on. So there are many applications where machine learning is going to impact the healthcare of the future. Some of the biggest advances in the short term are going to be those that make use of imaging data, such as computational pathology or radiology applications. But my research has been looking at really how one could try to change much longer term healthcare through algorithms that can guide treatment decision making. So, for example, we've done some work recently where we can guide clinicians towards choosing an appropriate antibiotic for patients who have urinary tract infections. And also work on risk stratification, where we can take longitudinal data on patients across many years and use that to predict future disease onset and even think about which patients are going to respond best to which treatment using that longitudinal data. Now, if we think about really where AI is going to start interacting with both patients and with providers from a human-computer interaction perspective, I think a lot of work has to be done to create the avenues for this knowledge that we learn from historical data to really have an impact. And so my lab's been also doing work in that vein, and I'll just very briefly show you a screenshot of that in order to provide some motivation for the techniques I'll tell you about later today. So this is a new system that we just deployed at a big hospital here in Boston called Bethesda Deaconess Medical Center in their emergency department. And it completely replaces the way that notes are typically written by doctors in the emergency department, and doesn't just provide a better way of writing notes, but also provides many opportunities for AI to provide clinical decision making. And I'll show you one example of that today, and I'll then allude to future examples in a moment. So here what you see is how when a clinician is typing, we have autocomplete of clinical concepts, and then that autocomplete is surfacing information on the right-hand panel that we think is relevant for helping treat this patient at this point in time. That information includes, for example, clinical notes, procedures that are relevant to those conditions, and so on. And I'll come back to this in just a few minutes. So one of the first questions that we've been asking recently, or actually for many years now, is can we develop AI algorithms to help with reaching a differential diagnosis? And this is a long-standing challenge in the AI field, and I'll tell you about work that goes back to the 70s on this problem. but is really now applicable in the types of settings that I just showed you a second ago. Imagine now that a clinician is typing a note about a patient, they're entering in symptoms that the patient is reporting. Our algorithms are automatically structuring that data as the clinician is typing, and now we can be running an algorithm behind the scenes helping with the differential diagnosis process and displaying those results in the right-hand panel of the system I just showed you a second ago. So at its core, to do this well, we'd want to be able to reason about the possible conditions or diseases a patient might have. So for example, the patient might be having a migraine, but maybe some of the symptoms might be explained by Lyme disease. Maybe they have other conditions like endometriosis. There are also, of course, symptoms that the patient is reporting. And what we'd like to be able to do is to understand something about the relationship between diseases and symptoms. So for example, maybe migraines could cause headaches and nausea. Lyme disease might cause headaches and skin rash. Endometriosis might cause nausea and abdominal pain. Now, there's a very long history in the artificial intelligence field of trying to build these knowledge bases, but typically they are very manual approaches that are very time consuming. So for example, a well-known system called Quick Medical Reference that was developed in the late 80s was estimated to take over 15 person-years of work to develop this model with something like 500 conditions, diseases, and several thousand symptoms. Now, flash forward 20 years, knowledge bases of the sort that I just showed you are commonly used in products that you and I might be users of. So for example, if you go to Google today and you search for a symptom or a condition, on the right-hand side of the Google search results will be what they call the health panels, which give much of the information that I just alluded to a second ago. For example, for the condition migraine, it lists symptoms that might cause the migraine. Similarly for common cold. And Google very arduously developed this knowledge base in a somewhat similar way to what I just alluded to a second ago from Quick Medical Reference, with lots and lots of clinicians refining this data over time in order to have something which was very high quality and could be presented at a massive scale. Now, similar models are being used in symptom checkers. So you may have heard of symptom checkers like Babylon Health or Buoy or ADA, and all of these, they are systems where a patient would go and report a symptom, and then it asks another question, the patient answers that question, asks another question, answer that question. In that way, the system is eliciting symptoms from the patient and is doing this type of differential diagnosis behind the scenes. Again, there's an enormous engineering task that has to be done to develop the knowledge bases that drive these symptom checking systems. And their current accuracy leaves a lot to be desired. So this brings us to the broader question of how could we learn medical knowledge? And of course, that then begs the question of where is that medical knowledge today? That medical knowledge might arise from biological experiments or clinical trials. It might be written down in medical textbooks. And so one approach might be to say, okay, we could try to derive that medical knowledge directly from medical textbooks. In today's talk, I'm going to suggest an alternative approach based on that electronic medical record data that I described earlier. We're going to ask, can we try to learn a graph, for example, between symptoms and conditions directly from data on close to 300,000 patients from Beth Israel Deaconess Medical Center? We're going to take all patients who visited the emergency department between 2008 and 2013. And from their clinical notes, we're going to extract 150 of the most common conditions that are seen in electronic medical records for these patients. Sorry, for patients who visit this emergency department. And by the way, 150 conditions actually consist of a very long tail. So there are some very rare conditions already in that set. And 500 symptoms that are commonly seen with those conditions. At its core, this data could be represented in the following form, right? For every row, we have a patient, and we have a binary indicator of whether the patient has that condition. We have a binary indicator of whether the corresponding symptom was reported for that patient. And a question you should be having is, how did I get this? How did I derive this structured data from the electronic medical record? I'll come back to that towards the end of my talk. So once you have that data, then the method that we developed in this work from 2017 in my lab was to use a machine learning algorithm on a Bayesian network, in particular a Bayesian network whose conditional probability distributions are parameterized according to a noisy OR distribution. We're going to take the data and do maximum likelihood estimation of the parameters of this model from that data. And then we're going to learn the graph structure relating conditions to symptoms by thresholding the parameters of the model. So for example, for every condition J and every symptom I, we have what's called a failure probability Fij, and small values of Fij denote edges that are likely to exist. So here's some examples of what we learned by using this completely unsupervised learning approach. So for example, in the second row, you see the condition appendicitis. And what I'm showing you are symptoms that our algorithm learns to associate with appendicitis. Things like pain, nausea, abdominal pain, tenderness, chills, diarrhea, vomiting, loss of appetite, lower abdominal pain, cramping, constipation, discomfort. You can next look at bed bug bite. You see skin rash, itching, anxiety, infection, carpal tunnel syndrome, numbness, pain, hand pain, weakness, arm pain, and so on. And this is just a very small subset of the 150 different conditions that we learned using this approach. Now, to evaluate it, we, in partnership with Google, they were kind enough to give us access to their knowledge graph, their health knowledge graph, which we used as a ground truth in our evaluation to see where we're able to recover the same graph, but using this automated approach. And so we would then take our graph or the parameters of the model that I just showed you, we're going to threshold them in order to get a graph and then ask sort of what fraction of the edges we've correctly learned. And using that, we can find that I only told you about one method, the noisy OR method, but we compare it to a number of other baselines. And our method does reasonably well. So in some sense, we can get reasonably high recall with precisions that are something around like 0.3. If you think about it, if you think about this as a first step followed by some manual refinement, actually that's not too bad. Turns out the story is a little bit better still. So we then did a clinical evaluation, recognizing that the health knowledge graph from Google might have actually been a bit incomplete, and we found that in fact the numbers were still a bit better. So this is a very promising approach for automatically extracting a knowledge graph from electronic medical records. Despite its simplicity, it seems to work pretty well. Now, that's only one type of knowledge. The next question I want to ask is, can we learn to connect conditions or diseases with other parts of patients' health information? And the motivation for this is a desire to be able to organize a patient's health record into what we call problem-oriented views. So for example, if any of you have an Apple phone, there's an application in it called Health Records that allows you to connect your phone to the electronic medical record of health institutions that you visit and download all of the data to your phone. And right now it's organized in a way which is a bit difficult to explore. So you have, say, lists of conditions, lists of medications, lists of lab test results, organized just in chronological order. What we'd like to ask is, can we find better ways to organize that health data in terms of actual underlying conditions? So a patient might have diabetes, hypertension, and breast cancer, and we'd like to be able to separate out the data for each one of those conditions. Another motivation for doing so, if you think back to the new electronic medical record that I showed you earlier that my lab has been developing, one of the things that we populate on the right-hand panel are these cards. For example, what I'm showing you here is a card for congestive heart failure, where again, we'd like to show just the data that's relevant for managing patient with congestive heart failure. Like, for example, the blood test results that you would like to follow, clinical notes that are referring to procedures and medications that are relevant for managing a patient with congestive heart failure, and so on. So the question is, how do we automatically derive these problem-oriented displays? And if we could do that, it's been shown that it can actually give a substantial reduction in medical errors. So we'd like to be able to get a graph that looks a bit like this. In red here, I'm showing the problems or conditions or diseases. Those are 3 different words I'll use to describe them. In orange are the medications that are relevant for managing a patient with that problem or condition. In blue are the procedures. In green are laboratory test results. And we'd like to be able to learn these relationships. Now, there have been decades of work on developing medical ontologies, such as what's known as the UMLS, or Unified Medical Language System. But these medical ontologies tend to be very incomplete, and they also tend to not be very accurate when wanting to be used for particular applications. So for example, what we mean by relevance here is we want to be able to find medications that are relevant for managing a patient with this condition when they present at an emergency department. And that notion of relevance with that context is very different from relevance in a different context. So our approach here is going to be to label some data and then to treat this as knowledge graph completion. And we're also going to show how to use pre-trained embeddings of medical concepts in that learning approach. So to construct the initial graph, together with 3 emergency medicine physicians, we took 32 common problems and conditions seen in patients who present to the emergency department. And we annotated medications, labs, and procedures for the relevance to those problems, receiving a total of 1,700 positive and 5,000 negative annotations, each of those done several times by each of the physicians. So this is pretty high quality annotated data. And I'd like to point out that the annotations are all available for free on our GitHub repository. This is work that was done in collaboration with ASAP. So that was to get an initial labeling of an initial subgraph that we're going to use within a graph completion approach. But I mentioned how also important here is to get good embeddings of the medical concepts. To do that, we made use of embeddings that my lab at MIT developed back in 2015, 2016. These embeddings of medical concepts we learned from a health insurance claims data set of 4 million patients, where for each patient you have across time procedures that were performed, medications that were prescribed, and so on. And we used a word-to-vec-like algorithm in order to learn a high-dimensional representation of all of these concepts. So for example, here I'm showing you both medications and conditions. And when you look for nearest neighbors in this space, actually they make a lot of sense. So they're not yet good enough for getting the relations, but they're a very good starting point. In order to refine it now, we used a well-known approach for knowledge graph completion, known as this DIST-MALT model that was published by Yang et al. In iClear in 2015. And what this approach will do is it'll attempt to learn for every potential edge in the graph a score that denotes how likely that edge is to exist. And so the way that this works is it takes as input a tensor where you have an embedding for each concept. And so that's going to be, for example, a condition embedding, a medication embedding, a procedure embedding, and so on. And it also takes into account a relation type so that we can take consideration that some edges exist because of that relation. And then it learns to predict a score. We used this approach and together with the embeddings that I showed you earlier, and it worked reasonably well. So here I'm showing you the mean reciprocal rank for if you were to take a new condition, so not one of the ones that was used during training, but a completely new one. So for example, sleep apnea was not used during training, but we're now going to ask, could we predict what the medications, procedures, and labs that are relevant for sleep apnea are? And we find that if you were to just take frozen embeddings and simply learn that relation embedding together with this DIST-MALT model, then if you were to use those pre-trained embeddings that I showed you earlier, you get a mean reciprocal rank of 0.268. If you were to instead try to learn new, what we call site-specific embeddings that were coming from a electronic medical record where we actually wanted to apply this technique, the performance was quite a bit worse because it was much less data. As you start to train the embeddings now, the mean reciprocal rank goes up much better. And just to mention as a side point, a challenge that one often faces when trying to use pre-trained embeddings for this knowledge graph completion type problem is that the pre-trained embeddings might not include all concepts that you care about. And so what we found worked really well was to use a k-nearest neighbor type approach, where if you have a data set that has concepts that weren't present in your pre-trained embeddings, you learn another embedding using that data set. That embedding, because that data set might have not enough data, might not have a very good distance metric, but locally it might be good enough. So what you do is you try to find nearest neighbors in the new data of concepts that were present in the pre-trained embeddings, and then use that to impute what the embeddings would be in the new data. And the details are in this paper. So I'm finishing up now, and there should be plenty of time for questions. But I want to close with the following broader question of how can we improve learning of medical knowledge? The algorithms that I've presented to you so far, I view as just strawmans. So they're very simple approaches from a machine learning perspective that do pretty well, but are really just scratching the surface of what I think we could potentially learn with better algorithms. So what are the limitations, and where should the field be going moving forward? Well, let's first look at the electronic medical records data that I spoke about earlier. There was a critical step in what I described where I said we extracted medical concepts such as conditions and symptoms from the clinical notes, and when you use that to derive this matrix of for every row of patients and which conditions and symptoms were present for that patient. Well, how did we extract those conditions from the clinical notes? Turns out that is itself a very hard problem, and a problem that the clinical NLP community has been tackling for decades, but with very little success, arguably. So for example, if one were to look at the most recent N2C2 normalization challenge, where there were over 100 submissions, the highest accuracy achieved at extracting and normalizing medical concepts from clinical notes was something like 85% overall. So if you look at the most common concepts that are very frequently occurring in clinical notes, they do pretty well, like 95% accuracy. But that drops very quickly to rarer concepts that might not be labeled in these very small label data sets. And so this is a major obstacle to being able to extract the knowledge that I just described from electronic medical records. And I think the only path forward here is to start to get some better labeled data. So in that vein, my lab has been developing a new annotation platform. Because of the massive scale of clinical concepts, there are over a million medical concepts you might want to extract and label. We need some amount of decision support for the annotators. And so we developed this tool with some decision support driven by machine learning. And we did an evaluation recently and showed that the machine learning that's used to help narrow down the set of choices to annotate actually doesn't bias results too much. And the next step is to start to scale this up. So what I'd like to be able to do is take publicly available data set such as Mimic, which includes clinical notes from patients in intensive care units, and annotate all 50,000 patients' clinical notes for clinical concepts and relations as a step towards starting to improve our ability to learn medical knowledge from electronic health records. And I'd love collaboration on that project, and please reach out to me if you're interested. Now, that's only one form of medical knowledge. There's also a huge amount of medical knowledge encoded in Wikipedia, medical textbooks, PubMed articles describing the outcomes of clinical trials, and so on. So I think the second direction that I'd love for the field to start working on is to ask, how can we take massive language models, such as GPT-3, A21i, and so on, which you could think about as a compression of this large amounts of publicly available data, and how can we think about extracting medical knowledge from those large-scale language models and using them for some of the tasks that I showed you earlier. Part of what gets me really excited about this research direction is that up until now, I've been unable to make use of publicly available knowledge repositories. So for example, I would have loved to have been able to do a Google search for a disease and for a sentence fragment that I see in an electronic medical record in order to extract medical knowledge from web pages. However, because clinical data has protected health information, we cannot simply do a Google search with that clinical note. And so it hasn't been possible to to make use of that publicly available data. But these massive language models now provide that opportunity. I can try to bring them internally to where I have the large health data sets and start to do some of these things that I've been alluding to. So that's it. I'm looking forward to your questions.
Dante, you're muted.
Oh, sorry. Yeah, thanks, Debbie. Yeah, I didn't know I'm muted. Yeah, so we have time for a couple of questions. Yes, so there are a few interesting questions on Slido. So the first question is, regarding the analysis of the medical notes, does the system recognize when a symptom is mentioned in the notes, but the mention is a negation, such as the patient did not show signs of?
Yeah, so it does, doesn't necessarily do so very well. The way that most systems for this work today are relatively simplistic. So there are a number of negation words such as not, does not, negated, like there, and what one would do is they will use simple rules in order to see, do these negation words appear in front of the symptom? If so, then we're going to say that symptom was negated. As you can imagine, that's not very accurate, and the NLP community has for a long time been developing better methods for negation detection, for hedge detection, and so on. One of the big challenges that the field has is that it's very hard to develop these machine learning-based approaches in a way which is generalizable across different types of clinical text. And the lack of availability of publicly available data and annotated data has really been a showstopper for the field. But there's a second problem, which is even more substantial from my perspective, which is that a clinician will often not write something. So sort of absence of information could also imply that something is negated, right? So they might not have a symptom and the doctor, instead of writing does not have it, simply doesn't mention it at all. And so in order to really go the next mile for this type of knowledge extraction, we need to build algorithms that can also understand the lack of mentions as a possible negation and can really disentangle those two things.
Great, thanks. The next question is a system capable of handling comorbidities?
Yes.
Do you want to say a few more words here?
Sure. So I view there being two important steps towards, for example, this differential diagnosis type system that I alluded to. The first step is learning the relations, so the knowledge graph itself. And the second step is actually using that for a downstream diagnostic purpose. Both cases have to take into consideration comorbidities. In the graph learning stage, because of the fact that we are only looking at mentions of symptoms and mentions of conditions anywhere in the note, but not necessarily in the same sentence, you have to worry that you might make false associations. And that's one of the reasons that the noisy OR model works so much better than some of the baselines that we mentioned, because it's able to disentangle some of those quantities. To do the second task, one wants to be able to model the joint distribution over conditions, recognizing that patient who has one condition is perhaps more likely to have another condition as well. And I view that as one of the next frontiers of what type of knowledge one would like to be able to learn from these large knowledge bases. That suffers also from the problem I alluded to a second ago, which is that you might have very incomplete information mentioned in the medical records.
Okay, thanks. So the next question is, so autocomplete feature is interesting and very impressive. I assume that it not only completes the text string, but also performs anti-linking.
Yes,
does this mean that the entity co-occurrence models also play a role? Does the user have the opportunity to edit linkage when an ambiguous mention is typed?
Yes, to the second question. So yes, it performs entity linkage as well. This is something that I only flashed in front of this audience, but we have a paper that's coming out in WIST, UIST, in the next week that goes into detail on this, and it's on archive already. The part of why I'm so excited about that autocomplete feature is because it provides a avenue for collecting much higher quality data from electronic medical records in order to do that type of knowledge-based creation and try to skip past some of the NLP problems that I've been alluding to for the last 5 minutes. So yes, it performs entity linkage. The users do have, there's transparency on what the entity linkage was, and the users can easily edit it if something was wrong. They can also help with the disambiguation process while they're typing. And in terms of entity co-occurrence models, we use machine learning algorithms behind the scenes that both take a patient's past electronic medical record data and the note as it's being written in order to predict what that entity is likely to be, which is what makes it very efficient from a user perspective.
Thanks. Okay, so next question. Do you expect to find in EHRs relations between disease and symptoms and procedures that are not documented in textbooks and science articles?
That's a great question. I think it's a really important question for all of us to be thinking about. Sort of what can you get from one place versus the other? I'd say in medical textbooks, you're likely to have quite a few of the symptoms that we're mentioning in those textbooks. What I view as a major blocker is that the way that they're mentioned in textbooks is not grounded in the way that they're mentioned in notes themselves, right? So in some sense, if we want to be able to make use of textbooks by themselves, we have to solve a linkage problem, which is recognizing that this symptom that's mentioned in the textbook is the same thing as this symptom mentioned in notes. When you start to learn these models directly from the notes, you can skip that problem altogether because you're already grounded in the way that the things would be mentioned in notes. That said, I think it's going to be really important to bring these together long-term. And the reason why is because there are a lot of rare conditions that you will see in the emergency department, among other places, where you might only see them 1, 2, or 3 times in the course of a decade. And so it's going to be very hard to learn the corresponding knowledge from electronic medical record data, despite the fact that if you had lots of it, it'll be better calibrated. You just don't have enough of it. So that's where you really will need to bring in that textbook type information.
Okay, we have time for one last question. So would you consider using methods that use medical guideline encodings in some structured formats, such as ontologies in your work?
Absolutely. Part of what I alluded to on the second slide when I talked about where machine learning is going to be used in the future was improving treatment guidance for clinicians. Now, that treatment guidance could be coming from a machine learning algorithm, which is predicting what would happen to a patient if you were to give them one treatment or another, and using that then to guide the suggestion. But it could also be coming from best practices that are encoded as medical guidelines in lots of published articles, among other places. And we really can't, we can't emphasize more the importance of even just getting the clinical community to use existing guidelines and best practices. And so I think algorithms that could try to infer medical guidelines from existing data, thinking about that as a form of health knowledge, and using that then once it's inferred without medical knowledge, without machine learning, using that to help guide some of those treatment suggestions within electronic medical records would be hugely impactful.
Great. So let's thank David. So we still have time to have interactions with David on the gather town session. Okay.
Thanks very much.
Yeah, thanks. Thanks for coming. Yeah. So next we are going to have a spotlight session, which consists of 6 talks, which will be presented later today.
My name is Christian Meilicke, and I want to talk to you about a paper, Why a Naive Way to Combine Symbolic and Latent Knowledge-Based Completion Works Surprisingly Well. On the right here, you can see a knowledge graph about Australia, and that knowledge graph misses some information. It's not known what is the capital of Australia, as you can see here. Now, knowledge graph completion is about finding candidates for that capital, finding a candidate ranking where the capital that you search for is hopefully on the top position. And methods that are these days used for this purpose, they all build on the notion of knowledge graph embeddings. They take this graph and map it into a multidimensional vector space, and then they do some computations which are not topic of the paper, and at the end you come up with such a ranking. Opposed to this, there are still some people using symbolic approaches, and I'm one of them. And these symbolic approaches might be rule learning approaches that create rules, that learn rules which reflect the regularities in the graphs. And obviously, these rules can then be used to also come up with such candidate rankings. Now, in our work, we are concerned with a method that combines the output of both of these techniques into a combined ranking. And you can see the MRR of complex E, the MRR of the rule learning system, and the combined ranking is depicted here. And you can see there is a significant improvement, I would say. And the good thing is that this is not only the case for a specific data set or a specific combination of data set and model. It worked in all our experiments over all of these combinations, as you can see. Now, well, I didn't really tell you why our method works, and I also didn't tell you how it works. If you want to know that, I'm happy to talk to you in the poster session about these topics. Thanks.
Hi, this is Michael Bugert from UKP Lab in Darmstadt, Germany, and we are presenting work on a new data acquisition strategy for event coreference resolution. The task of event coreference resolution consists of two steps. First, we want to find mentions of real-world events in text, and then we want to determine which of these mentions refer to the same event. On the left side here, you can see an example involving a single document, but what we are specifically interested in is the cross-document case, where coreference is possible between mentions from different documents. The variation of this task is difficult due to the large number of mentions that need to be considered at the same time, on top of the fact that event-related tasks already tend to be quite difficult on their own. Now, the large number of mentions also affects data annotation, which is particularly expensive and time-consuming for cross-document coreference. So the question becomes, how can we avoid these costs when creating data? And what we propose is to automatically extract data from hyperlinks in online news. And here's how it works. So on the left, we have a news article containing a hyperlink, and this hyperlink references another article, which itself describes an event. So basically, this underlinked hyperlink anchor text, the blue portion, becomes an event mention of that event. And if we now manage to find a second news article also referencing that third article, we get a second event mention, and by that we get an implicit cross-document event coreference link. So this is the solution we propose. It is a bit noisy, but it's still much faster and cheaper than manual annotation would be. So is it useful? Yes, we trained a system on hyperlink data and on gold data, and the systems were very close in performance. If you'd like to know more about our work, then please come and visit us in Gathertown. Thanks.
CAT. Weakly supervised text classification with naturally annotated resources. This paper proposes a large-scale resource for building general-purpose text classifiers. NatCat is constructed from 3 data sources: Wikipedia, Stack Exchange, and Reddit. NatCat consists of document category pairs derived from manual curation that occurs naturally within online communities. Here is an instance from NatCat Wikipedia, with text and 1 positive category. We can use NatCats to construct general-purpose classifiers. In our paper, we built text classifiers to score any document category pairs from NatCat. The trained models can be directly applied to any text classification tasks by treating the given labels as a scoring and ranking task. The text can also be scored against all NatCat categories, and the top scored categories are good labels for the text. NatCat is a large-scale resource with over 1 million categories and 10 million documents. 3 data sources exhibit different characteristics. Wikipedia contains over 1 million categories with a diverse set of topics. Stack Exchange only has 156 more focused categories. Reddit categories are colloquial and noisy, so we only use the most frequent 3,000 categories in NatCat. We use NatCat to train BERT and RoBERT models. The models take the category name and some text, and output a score. Comparing these models with the explicit semantic analysis from data list classification, the NatCat trained models are stronger on topical and sentiment classification tasks. Overall, we find NatCat is better at topical classification than sentiment tasks.
My name is Leandra and I'll present you our paper, Prompt Tuning or Fine-Tuning, Investigating Relation and Knowledge in Pre-trained Language Models. This is a co-work with Jan-Christoph Carlo and Wolf Thilo Barke. So first of all, Petroni et al. Have shown us that you can extract relational knowledge from pre-trained language models. This is possible with so-called closed-style queries. So for example, considering the triple fact Berlin, country, Germany, then you can use a prompt and formulate the sentence Berlin lies in mask. And in this case, Bert should find the most suitable token for this mask token. And yeah, Bert is happy because he predicts the correct token Germany. But what about those prompts? So we have these manually created prompts of Petroni et al., subject lies in object. But there can be many other prompts which might be even better. For example, subject lies in the country of object. And of course, there's the question, which one is the best? And there's much research in this field of prompt tuning, but this requires much training data. And so our approach is quite different. We don't tune the prompts, we rather use simple prompts, which are reduced to the label of a relation. So for example, subject, country, object. So there aren't whole sentences anymore, and for this to work well, we fine-tune the language model. As a result, our approach by triple outperforms all the baselines significantly with a precision of about 48%, in contrast to the best precision of the baselines with 43%. Additionally, it requires less training data. These results are quite interesting, and we are looking forward to discuss with you in the poster session how these new findings impact the research in language models. See you!
Hello everyone, I'm happy to be presenting our work, a joint training framework for open world knowledge graph embeddings. I briefly present our motivation. In the recent years, knowledge graph embeddings have emerged as a popular way to encode information for a variety of downstream NLP tasks. As knowledge graphs expand, we are presented with new entities, often with their textual descriptions. So applications that rely on KG embeddings require approaches to embed these new entities using their descriptions. We would like any such approach to learn embeddings for the new entities. We want the triple scoring function of any such approach to be efficient and hence also the ranking. We want any such approach to work with a variety of knowledge graph data sets, regardless of the description length. And most importantly, we want our modules to be trained jointly, as recent studies have shown that such approaches have significantly improved geometric properties. Here, we present the overall framework of our method. Chiefly, we have three modules: the description encoding module, the KG embedding module, and the projection module. Our method utilizes a KG embedding loss term, a projection loss term, a cross-domain KG completion loss term, and finally, when our descriptions are short, we encode them by averaging their word-to-vec embeddings and train folk by minimizing this loss. When our descriptions are long, we encode them using the transformer model Roberta. And since transformer models take a while to train, we spread the training out into two phases. Here we present our results. We are happy to report that folk outperforms all baselines across the three datasets, and we obtain an average mean reciprocal rank improvement of 35%. The same holds true when our descriptions are short. And here we also note that the two encoding techniques perform similarly. On the topic of geometric properties, also the embeddings induced using folk are significantly more homogeneous to the pre-existing KG embeddings, as opposed to the embeddings induced using a baseline OWE that clusters separately away from the structural knowledge graph embeddings. We also report two metrics, the eigenvalue similarity and the hubness. And here as well, we note the performance improvement of using folk. Please do stop by our poster session and reach out to us for more information. Thank you.
Okay, so just a couple of quick announcements. So now you can walk out of the room and go across the hall to the chats and posters room, and our invited speakers, Gia and David, will be there to chat with you if you have more questions. It was very interesting talks. And then immediately after that, without any break, we're going to have the social event. So as Andrew mentioned in the introduction, in the opening remarks, there's a long tradition of hikes in AKBC from the original AKBC. So here we cannot have that, but we do have a social event. So you can go to the room on the north corner of the entrance room, and different people like different things. So we have a few things there. First, there are games. You can play video games, a bunch of video games that are set up there. You can assemble a group and play together code names and other types of games. If you want to meet new friends, there's an area with intimate tables where you can sit, and this should signal that you are interested in perhaps having someone join you, and you can chat about your research interests and whatnot. And also we have larger tables for discussion groups with various topics. So if there's a topic you're interested in discussing with someone, you can go to that discussion group, and if a few people join, then you guys can discuss. So this will go on for about an hour, and in 1 hour and 37 minutes roughly from now, we will reconvene for the next invited talk. So have fun, and we will see you in the chats and posters in the social room. Okay, we are live. Okay. So it's my great honor to introduce our next speaker, Yolanda Gill. And Yolanda is Director of New Initiatives in AI and Data Science in USC's Viterbi School of Engineering and Research Professor in Computer Science and in Spatial Sciences. She's also the Director of Data Science Programs and of the USC Center for Knowledge-Powered Interdisciplinary Data Science. Her research is on intelligent interfaces for knowledge capture and discovery, which she investigates in projects concerning scientific discovery, knowledge-based planning, information analysis and assessment of trust, and more. And her talk today will focus on knowledge extraction from text for scientific purposes. She has also done very interesting work on developing computational tools for environmental sciences. She has many honors and is a fellow of the ACM, of AAAS, of IEEE, and AAAI, and recently served as its 24th president. So it's really a great honor for me to introduce Yolanda and to listen to her talk. So take it away.
Thank you, Samir. Thank you for the kind introduction, and thank you for inviting me to speak. I'm very excited to share with you some of the work that we've been doing on extracting knowledge about models and workflows in science. Our objective is to make science more transparent, reproducible, and when possible, automated so that AI can be more of a participant in science. I want to start by thanking a lot of my collaborators. There's too many to name. I'm sure there's many missing, and our sponsors. Science is very complex and every domain is different. So I'm very grateful to have a lot of projects where I can learn about different aspects of scientific knowledge. So I pose to you the question of whether AI will write the scientific papers of the future. And I believe it will. Humans, I have argued, make mistakes. We neglect to mention important things in our papers. Sometimes we're biased in the way that we interpret results. We want to confirm what we believe and not mention other possible interpretations. And there's a lot of times there's errors and mistakes, even paper retractions by Nobel Prize winners are an example of that. So I do believe that in the future, for most of scientific analysis, AI will be writing these papers and automating a lot of the analysis. What I show you here on the left is different projects that we've been working on to represent different kinds of scientific knowledge. Maybe some AI scientist in the middle, and then on the right, a scientific paper of the future. For me, this means that it's reproducible, it follows open science principles and digital scholarship practices. There's a nice paper on reproducible AI in AI Magazine where you can see some of the recommendations for AI in particular. So what would it take? What needs to go on the left side? What would this AI need to represent? And I want to share an example with you. This is work that we did some years ago on a paper on drug discovery that we were trying to reproduce. The paper talked about using the SMAP software to compare ligand binding sites, and it described the kind of data that they were using. And it looked like a step where you would just run that SMAP software. It turns out that when we went through the code and ran into a lot of problems, they actually run it twice with different subsets of the data. They actually did some alignment of the results. They actually did some filtering and ranking of the results. None of that was described in the paper, and without any of that, the results were not the same. So it took us 2 months to reproduce the work that seemed to be a week's worth of work by a student, and we required the expertise of the authors. So scientific papers really omit important steps. Sometimes they're inaccurate. Baggerly and Coombs, who are statisticians that work in cancer, call these processes forensic research. It's really a lot of work, a lot of detective work to find out what a paper does. So we've started to capture knowledge structures that allow us to generate portions of papers automatically. This is interesting work that we're doing, paraphrasing workflows and provenance records. But there's a lot more to do in this space for AI to write these papers. So what would need to be represented in order to automatically generate a paper, at least the method section, so that we can report accurately the analysis and the findings? The benefits is that, of course, the writing is accurate. You can customize the description to different audiences, someone that wants a high-level picture, someone that wants an emphasis on data, someone that wants an emphasis on the software used, and the details of how things were run. It's easy to update if there's new data. It's easy to reuse by others. You can look at what-if scenarios, what if we had tried different settings or parameters, and we can compare easily with other work. But also, from my point of view, AI could be used to try to do novel work, try to do novel explorations, and also develop new methods and more creative approaches to science eventually. So we talk about doing these data analysis, and I want to focus on scientific models. They are ubiquitous and very, very hard to use. So we've been working on problems of food insecurity in Ethiopia, flooding in Texas, sustainability in California. And what you find is that they require integrating a lot of scientific models, and just using one scientific model takes a lot of work, and it takes just a lot of expertise and reading and finding out what the model is about. So these efforts take years to put together a picture of what's happening in an area, and it doesn't leave a lot of room for developing scenarios or trying different options. So how can we capture knowledge about these models so that we can automate the process of running them and showing results? So we've been developing ontologies over the years that give us a target of the kinds of knowledge that we need. This is our more recent one, the model metadata ontology. It's building on a software description ontology. These ontologies don't focus so much on computational properties, but more on the scientific properties of the models in addition. And what we can do when we have all this information is to automate a lot of the processes and help users look at options and what-if scenarios and picking the best model for their purposes. And on the left, you see a visualization of potential flooding and road blocking in South Sudan. So a more recent project, we've been using this knowledge about models to recommend models for control fires in certain areas. You know about the big problem with mega fires. If we do control fires ahead of time, then we can avoid for wildfires to get out of control. So what we're doing is represent a lot of information and metadata about models. Models have many variants. We represent metadata about all of those variants, so we can make recommendations and check constraints for models and recommend for users the best model for their particular area that they want to do a controlled burn. So there's a lot of great use for scientific software and metadata. I want to share with you some work that we've done on extracting this metadata by hand and fitting it into our ontologies, and then some more recent work on automatically extracting this metadata in an area where I hope that this community can help us a lot with. So for manual extraction of scientific software metadata, we targeted requirements from a set of diverse scientists. These were including hydrologists, volcanologists, oceanographers, all kinds of areas in science. And they told us what they look for in software as a scientist. So they had 6 different categories. And when the metadata was populated, they could actually compare and contrast different models and see what suit their problem better. So this was our target ontology to fit. So I'm going to describe the work by Bakina Messawi on her PhD thesis on extracting metadata for 15 pieces of code that were pre-processing data to run a hydrology model called VIC. So each step, each of the 15 codes is publicly available. 13 are published in Zenodo, and they have decent metadata, and 2 are published in the model website. Could we find all of these metadata characteristics for all of these codes, was the question pursued in this work. So it turns out that a lot of information about all of these codes is not in papers. So oftentimes these are considered ancillary software. There's a lot of papers about the model, and all that metadata is very challenging to get. But for these smaller pieces of software, we thought it might be more tractable. They're not mentioned in papers. So we have source code. We have the model's website that describes some of these software and why it's needed, the entry for the software in Zenodo, the documentation that the model has, and then there's also a user discussion wiki. And so you can see, for example, at the bottom left, a README file that has some of the information. And then on the right, you can see in total where the information, this metadata, ended up being in terms of the source that we use to get the information. So all of those 5 sources seem to be complementary. So by hand, we populated all of this metadata. We created this knowledge graph that you see on the right side. And then on the left, kind of the browser that we used in showing all of this metadata so they could see it and compare. For these 15 pieces of software. You can access it in the Ontosoft website. And so you can see that this is the same picture showing the source that was used to get the metadata. And then by the 6 categories in the ontology, there's actually more information in some sources versus others. So it's interesting that all of these sources of information about software contain different types of metadata that is useful. And you can read a lot more in the paper. One interesting thing to share with you is that for software 11 and 12, 2 of the codes, there's a lot less metadata that was found in any of those sources. The others were pretty complete, but these 2 are the codes that were not in Zenodo. So a lot of the documentation and information was very incomplete. So the paper has a lot more details about this. So it looks like the information about software is available out there in various shapes and forms. Can we extract it automatically? So I want to talk about some work done by Daniel Garijo and other collaborators on SOMEF. So it's a software for metadata extraction for scientific software. Daniel has been looking at machine learning software, model software, all kinds of software, and starting with those that have a GitHub repository and look at README files, looking at files that are included like notebooks and Docker files, also using the GitHub API for some of the metadata, and then populating the ontologies. He's using Code Meta, which is a community, I wouldn't say standard, but it's a community ontology for software metadata. And so you can see that he's been trying different approaches to extracting different metadata categories. So sometimes he'll take paragraphs and classify what type of metadata that paragraph may contain. So he does this as binary classifiers. He'll do header analysis and sentence comparison for some other fields. Sometimes he'll look at regular expressions that appear in README files to extract certain metadata. Other times we're lucky and there's a GitHub API that provides that metadata, for example, the license and the ratings and the programming language. So lots of work to do in this respect, but extracting metadata for software is very, very useful. We face many challenges, and I hope that this community will be excited to work with us in pursuing these topics. So a lot of knowledge about models needs to be extracted. So I've told you about model software metadata. Depending on whether you just want to browse, compare, and select a model versus automate some workflow, or maybe adapt a model for your own purposes, the metadata that you need is very different. So there's different target ontologies and different target uses for this. We want to also think about the workflow data flow. So not just extract metadata for one given step, but make sure that it is consistent with the metadata for other steps, and make sure that what we understand the data flow is consistent across all the steps. We want to also be able to take this software and set it up for automated testing and execution, so that we can have AI systems that start to consider the software usable and run it in different scenarios and circumstances. Models, just like machine learning models in hydrology or agriculture or other areas, they have calibration and training procedures. So it's really important to capture those workflows or procedures for models. So much knowledge about models needs to be extracted. I think we often focus on metadata for scientific data sets. I think we often focus on extracting from the literature knowledge about entities like proteins or genes and so on, and their biological processes. But I think that this area has received a lot less attention. I think we also want to be able to distinguish and yet connect related models. So our dream is to be able to say, here's a collection of 20 FIRE models that we found on GitHub, and how they're related and how they're different, and how you could run them together, and how you could try different scenarios with all of them or most of them. Really composing workflows with several models and running integrated analysis. This is something that's very needed in science. As I said, it will take 2 or 3 years to do this by hand, because all of this information is so scattered, and very few know where to find it and how and when it's needed and who needed to know. And then eventually be able to automatically write the methods section on papers in a way that is customized and includes all the information properly and accurately. So I will leave you with this question of, will AI write the scientific papers of the future, and the advantages that that would have in terms of accurately reporting what work was done, customizing the paper to the level or the detail or the discipline of the reader, being able to update the results if new data is available, reusing parts of the analysis for other purposes, look at what ifs in the settings of the experiments, and comparing different experiments together. There's many benefits to this. And then, really the holy grail is for AI systems to be able to do novel work, test their own hypotheses, their own analysis, and then try new creative approaches to science, maybe new methods or new approaches to answering questions. So what would we need to represent in order to enable AI to automatically generate these papers? So today I told you about what we've needed to represent about models. It's a very, very rich area with high payoff in terms of automating science. I'll stop here and take questions.
Okay, thank you, Yolanda, for this talk.
Okay.
We do have many questions from the audience, so they should appear soon. So here's, I'll jump right in. So you were talking about extracting software metadata. How much of it is actually from natural language text?
Most of it is. Most of it is. So we are beginning to read through code. This is very hard. When you read through code, you really get ambitious because you realize that the input to software is certain files and certain formats. But really, the input to these models is these physical variables that you're going to simulate. And that's very important knowledge to extract. So you can get some very useful information from code, but most of the metadata that we extract and that the scientists read when they're trying to understand a model is just plain text. And as I said, it comes from any of these 5 sources. So the documentation of the code, maybe having run the code before, you just know how it works, or you see it in the code itself. The entries that you see in shared or public websites, project websites as well, and then discussion forums. And there's many of those for many models in particular.
So just as a follow-up, like, how do you said how do you even know that you've extracted enough metadata to, let's say, write like the method section of a paper? Like, when do you know that you have all the information?
So, I mean, this is really my question to you, right? So we are, our latest ontology that describes what we need to be able to run these methods automatically. So we run models in ensembles, running different scenarios, different settings. We can run them for different regions. So this is a pretty complete ontology for us. So this would be kind of the target. There's always more. So for example, we still don't have a good ontology for model calibration or model training. We need to describe those processes better and more explicitly. So that's certainly future work. So as I said, depending on your purpose and the breadth of what you want to cover, you may need additional metadata. But this particular ontology, you can see the URL here, is quite comprehensive in terms of being able to automatically run a model and run it with different scenarios and regions and data.
Thank you. We have an interesting question from Jason. I'll just read it out loud. You presented a very neat vision. Thank you. I wonder how far GitHub or similar organizations are invested in pushing this vision. Can you share your thoughts on how to engage the industry on this?
Yeah, that's a really good question. So, so the last 10 years or so, I would say, there's been tremendous movement towards open science and shared digital objects. It all comes down to the cost of documenting all of these scientific objects that we want to reuse and understand and compare and eventually, for us in AI, automate some of these processes. And it's a big ask from scientists. So think about yourselves when you're running machine learning models or you're writing your papers. It's a big ask to document and publish all of your software explicitly. To put, when you write a paper, you need to not just give a pointer to your GitHub, but give a pointer to the particular version of the software that you have used in your paper. Because, of course, your software site may have many versions and it may be very ambiguous. So it's quite a bit of burden on researchers to really document their papers. You're asking about GitHub and industry contributors. So publishers are very invested in publishing papers that really contain a lot of this information. It's just very hard to raise the bar because then authors will go publish in other places where that bar is not as high. As I said, it's quite a bit of overhead. An entity like GitHub, I don't want to speak with them, but I can tell you that Code Meta was a community effort to compile a minimum set of software metadata requirements for all sites. So we had lots of representatives from data repositories, from Figshare, Zenodo. Figshare was public at the time. GitHub was also represented, and kind of what would be the basic metadata. When you do that, that's one flavor of metadata, right? That's good for repositories and tracking who was the author and the date of creation and a unique version, but it doesn't help us in terms of automating the execution of that code or discovering it or comparing it to other software. So I know that there's a lot of interest, but all of this metadata comes at a cost. So that's why automating the extraction of the metadata from the documentation that scientists do write for other humans to consume may be a very important direction to pursue, because for scientists to provide it by hand, it's really a big ask.
Thank you. And let's say that we were able to perfectly extract all the metadata according to the ontology. Is that already sufficient to write the methods section, or are there still missing things?
So as I said, I posed this question as a long-term question. We have focused on ontologies that help us. I'll show you. So OntoSoft, for example, was an ontology that helps scientists compare, for them to find models, compare them, browse their characteristics, and select one. And so it's metadata that gives you a roadmap from your problem to the best model that can help you solve it. That is one type of metadata. The other metadata ontology I've shown is the SDO ontology, which focuses on being able to run the models and being able to use them with different inputs, different scenarios, be able to have different configurations or settings of the same model. So this helps us run ensembles and run models in different circumstances, in different scenarios. But to really write the section, the method section of a paper, we have a lot more work to do, right? So you need to be able to describe all the data preparation workflows, all the model settings. You need to show model calibration and training procedures. We don't really have ontologies or target metadata for these yet. So we are a ways from being able to generate the method section of papers. What we have done is generate parts of the method section. So we can take, for example, a workflow of many steps and describe the data that was used. Sometimes scientists are interested to see what data sources were used and whether it was daily data or twice daily data. So we can describe the data sets, or we can describe a whole workflow based on the major steps, or we can describe all the steps, no matter how small or accessory. So we've been working on narrating a workflow that's already there. But there's a lot more metadata and knowledge involved in the method section of papers. So a lot of work to do yet to generate that. Think about model calibration, right? How would you describe that? What knowledge structures would you use to describe model training or a model training procedure or a model calibration? It's not an easy thing to describe.
I can imagine this can become hairy very fast. We have time for more questions, I think. So Subu asks, once the metadata is extracted, how would you convert them into natural language text for the paper? And how would you compare model errors introduced there compared to human errors? Do you have any thoughts on the generation to natural language?
Yes. So Indeed, this is a very interesting question because a lot of the metadata could be erroneous. So I'm going to go back to this slide, and I'm sorry that it's so small. The point of it is that
maybe just Samir can put your screen back. Okay, thank you. Now we see your screen.
Oh, okay. I had been going back to slides as I was talking. Thank you. So if I go back to this, these are different narratives corresponding to the same workflow, or the same set of steps of an analysis. And some of them are focused on the data that was used. Some of them were focused on the details of the software. They're focused on different things. We use a template-based approach. So we look at the description of the workflow and we follow templates to describe every step. I'm sure there's a lot more sophisticated language generation techniques to make the narratives a lot more fluid. But we had a student working on reading the narratives and detecting where they were incorrect. And so for a scientist to browse through a knowledge graph, or comparing software and detecting errors is a lot harder. But coming here and looking at what would appear in their paper. So the student looked at different segments of text produced by a template and changing some of the content of that narrative. And then that would get reflected in correcting the metadata. So I think that this would be a really interesting direction, that papers become correctable if, as often happens, somebody finds that something was erroneous.
Yeah, it does sound like there's a lot of room for collaboration between our communities. I think that's all the time we have for questions, but hopefully you can stay with us for the chats in an hour or so. Thank you very much for this very ambitious project.
Certainly, and thank you very much for having me.
Yeah, and Samir, we can. Okay, so Devi, we cannot see you yet, and I think you're muted. Okay, now everything is great.
Okay.
Okay, great. So our next speaker is Devi Parikh. So it's a pleasure for me to introduce her. So Devi is a research director at Facebook AI Research and an associate professor in the School of Interactive Computing at Georgia Tech. She received her PhD from CMU and was a research assistant professor at TTI. And she has really worked a lot at the intersection of vision and language, with foundational work in visual question answering, visual dialogue, pre-training language vision models, and working on human AI collaboration and embodied AI in 3D environments, and has a lot of interest in generative models for creativity. She's the recipient of numerous awards, and an Seth Currier Award, the HKI Computer and Thought Award, a Sloan Research Fellowship, and many more. She was also on Forbes' list of 20 incredible women advancing AI research. Her talk will pop up a bit, it seems, and will give us a broader perspective on language and vision. So I'm really curious to hear her thoughts. So you can go right ahead.
Thank you so much for that introduction. I am sharing my screen and I have pulled up my slides. Are you not seeing them?
Yeah, we see your slides.
Okay, great. So everything is good, right?
Yes. Yes, yes. I disappear very fast. So yes, the answer is yes.
Okay, sounds good. And I only see my slides, but I'm assuming that me and about language. And so, as the name suggests, these are problems at the intersection of computer vision and natural language processing. And so things like, given an image, can we automatically describe it in a sentence, in a caption? Given an image, can we identify local regions that are meaningful and describe each local region with a phrase? If I give you an image and if I give you a short phrase, can you ground the relevant part of the image that is associated with that phrase? Not just static images, but if I give you a video, can you generate either a detailed description of what is happening in the video or a short description that summarizes the key events, or maybe just even a single sentence description that just generally describes what's happening in the video. In addition to sort of passive description, where the machine gives you a description and you're stuck with whatever it is that it chooses to describe, can we also have more active ways of eliciting information from an image using natural language? So things like visual questions.
Debbie, I'm sorry to interrupt. Are you clicking? Like, are the slides moving? Because we see just the opening slide so far.
No, yeah, the slides are moving.
Okay, so we are not seeing that. Maybe Samir, can you help us?
I think the internet connection is just really bad, and maybe that's why this is happening. You want to try resharing, Debbie, and see if that makes a difference?
Yeah, let me try that.
Because even the audio is coming out a little bit distorted.
I see.
And the video is low quality, so I think it's just the bandwidth.
Let me try and apologize for that. Let me try and change my network and see if that is better.
Okay.
Sure. We have patience.
My phone's OS seems to have updated, so my personal hotspot is not set up anymore. I unfortunately don't have a quick way of changing the network. How bad is it?
I guess the main thing, like the slides were just like, we could not like, we saw just the opening slide. You want to try to reshare your screen?
Yeah. So I did reshare. Now this should be the opening slide. There should be the next slide. No?
Okay, so we can see it now. It might even help. Oh.
Should we turn off video?
Yeah, maybe we can try turning off Devi's video, I think. Yeah, but sure.
Let me try this again. So this should be the title slide. And let me know when you see a different slide.
Yeah, so we're seeing the full window right now.
Did you say that you're seeing the slides in full screen?
No, it's still windowed, and I think the audio has been coming in and out, so I've been barely catching you. Yeah.
I'll just give me 1 second. I'll be right back and try and do something.
Sure, yeah.
Always prepared.
Can you hear me?
Yes.
And does it seem like it's better?
The voice is better.
It's a little better. Yeah, the audio seems a little better. Yeah.
Okay. Let me try and share my, let me stop sharing. Let me share again. Do you see my title slide in full screen?
Yeah. Yeah. Let me switch now.
And
Okay.
do you see my next slide now? Okay.
Yeah, this seems better. Okay.
All right. Hopefully, apologies again, and hopefully this will stay
Great.
all
No
right.
worries. No worries.
Yeah.
You can just whenever you're ready.
Sorry, say that again.
You can start whenever you're ready.
Okay, sounds good. Thanks. Yeah, so I was describing problems at the intersection of vision and language, and I gave examples of image captioning, dense image captioning, referring expressions. So given a phrase, you want to ground it in an image, describing videos at various levels of detail, answering questions about images, maybe even having a back and forth in terms of a dialogue that is grounded in the content of an image, like you see here, and a variety of other problems in this space. And so the motivation behind why vision and language is interesting or is exciting is, I think, from a couple of different perspectives. One is in terms of demonstrating AI capabilities, this can be interesting. So, for example, if you want to demonstrate that the machine can understand language, one way of doing that could be to say that if you can ground these tokens, if you can ground these phrases or sentences in concrete things in the world, and one way of depicting the world is through visual data, then that's one way of demonstrating language understanding. And the flip is also true, that one way of demonstrating image understanding is to say that if you can describe various details of the visual content, then that's one way of demonstrating that the machine has some understanding of what's in the image. The other is sort of not just demonstrating AI capabilities, but improving them, right? That if you have visual data in addition to language, then you might be able to understand language better. You might be able to learn better representations of language. And the flip is also true, that if in addition to images, you also have rich natural language associated with it, then you might be able to learn richer representations of images and do better at a variety of computer vision tasks. And finally, it's sort of, even intellectually, it's nice if we can move towards models that aren't specific to individual modalities, but can deal with more than one modality at the same time, in this case, vision and language. So that's one set of motivations. And the other, more from an applied perspective, is that there are a variety of applications that can benefit from having models that can understand both modalities, vision and language. So for example, if you think of visually impaired users where the visual content is not as accessible, if we have a way of translating the visual content into language, then through language, they can have access to some information that they may not have had otherwise. If you think of all the visual data on the web that tends to be unstructured, trying to organize it, trying to navigate through it, natural language is a good interface to do that. If you want to learn information, if you want to extract information from the web, a lot of the information on the web is multimodal. And so being able to connect these two modalities would let you extract more information. Related, if you're trying to detect something like hateful content, it is often the case that any one modality on its own is probably fine. Like in this case, the image on its own is fine. The text, you smell good today, on its own is fine. But the combination of the two is problematic. And so if you want to detect that, you really need to be understanding the interactions between the two modalities. And if you think of sort of AR, VR applications, being able to navigate in a virtual world using language would be a useful thing. All right. So in these times where it feels like there's sort of a new AI revolution happening almost every week, this is an image generated by VQGAN plus clip for the phrase "a revolution every week." For anyone who's following along with these fun collab notebooks that get shared on Twitter, I thought that sort of with different architectures showing up, having better performance, it can be a little overwhelming. And so I thought it might be useful in this talk to sort of take a step back, and maybe I can draw out a little bit of the trajectory of how this space has evolved in the last, I don't know, decade or so, and then comment a little bit on what I think are interesting directions forward. And hopefully that will be useful to the audience here. All right, so let me do that. So this won't be, I should say that this won't be an exhaustive historical overview. It won't be referencing all the important papers or anything like that. These are just going to be a few hand-chosen things that lay the narrative out a little bit. And so here's one paper from 2010. It was called Every Picture Tells a Story, where the idea was they were looking at image and text retrieval. And so the idea was to start with an image, detect some objects, detect the context, the scene that it's in, and you have an associated corpus of language that you're seeing on the right in the form of these captions. And you're trying to extract the same concepts from language. And then in this meaning space that is shown in the middle, you're trying to align the two. Here's another paper that was one of my favorites from the time. It's called Baby Talk, where you have, and this was a language generation, and I'm putting language in air quotes because it wasn't natural language, but it was an image captioning task where you're given an image, and the approach that they used was they would run these independent object detectors. And so note that this was all before sort of deep learning had become as exciting as it is today. So these were what you would now call old school computer vision object detectors. So you run object detectors, you run for each one of those, you classify them into various attributes, you look at pair of objects and classify the relations in terms of prepositions. And then they built this conditional random field, a CRF, where you have these objects and attributes as nodes, and then you have these pairwise interactions as prepositions. You're running inference on this graphical model. And as a consequence of this, you then are able to produce this language. And so this language is very templated, and you're just sort of filling in various slots. And so in this case, the description is, this is a photograph of one person and one brown sofa and one dog. The person is against the brown sofa, and the dog is near the person and beside the brown sofa. So I remember I was at this talk, Tamara Berg had given this talk at CVPR 2011, and my mind was blown. I thought it was so cool that we could take as input an image and produce something that sounds like language and is describing the various content in it. And yeah, so that I thought was very exciting. And I will revisit this a couple of times in the rest of my talk today. And so going forward, around 2012, the AlexNet moment happened, and the ImageNet workshop, where deep convolutional neural networks got really high performance on the ImageNet classification task. And in his talk, Alex, the first author of this work, felt the need to have to explain to the audience what a neuron looks like, what a neural network looks like, because again, at this time, very few people were using neural networks. And then he goes on to explain convolutional neural networks in 1D, talks about convolution in 2D, and is sort of building everything up from there. And from that sort of moment on, as many of you I'm sure know, in a wide variety of computer vision applications, sort of the community started exploring what these neural networks can do for us, pre-training these representations, fine-tuning them on a variety of downstream tasks. And in parallel, we were seeing similar early indications in natural language processing as well. Many of you, I'm sure, are more familiar with this than I am, but my understanding is at the time for things like machine translation, we were starting to see some promising results. And so both in vision and in language, neural networks were starting to be effective. And so right around then, a year or two later, motivated by this, that in vision, we are seeing neural network models do well. In language, we were starting to see some promise as well. And so researchers at Microsoft who were building this COCO data set, where it was intended mainly for sort of core computer vision problems like object detection, segmentation, and things of that sort. They also decided to collect a data set of images and associated captions that they then publicly released for others to use. And so at the time, there were multiple groups that all at the same time started exploring this data set, trained image captioning models, and there were several submissions to CVPR that year. So this is November 2014. And there was one thing that happened at the time was there was this New York Times article, I think it was like the day after the CVPR deadline or something like that, talking about all the image captioning work that had happened. And so I think this was one of the first times computer vision was sort of getting this sort of visibility. There were a lot of concerns around hype associated with this, concerns around how not all groups that were working on this problem being represented here. And so that kind of shook things up and sort of brought vision and language quite a bit of attention at the time. But so back then, this is 2015, about sort of 6 years ago, we already started having models that can take an image like this and describe it as man in blue wetsuit is surfing on wave, a group of young people playing a game of frisbee, a car is parked in the middle of nowhere, a pot of broccoli on a stove, and so on, right? And so if you contrast it back to the example that I showed you from Baby Talk, which was just about 4 years ago, there the description was, here's another example. This picture shows one person, one grass, one chair, and one potted plant. The person is near the green grass and in the chair. The green grass is by the chair and near the potted plant. And so, yeah, it felt like things had come a long way where we have these much more natural sounding descriptions of images. And they were also more accurate, right? They weren't just natural sounding. But so here are a few failure examples from the Baby Talk paper. On the left, so this is 2011, on the left, the image was described as there are one road and one cat. The furry road is in the furry cat. The image in the middle, this is a picture of one tree, one road, and one person. The rusty tree is under the red road. I would actually think of that as a fairly creative description. The colorful person is near the rusty tree and under the red road. On the right is there are one potted plant, one tree, one dog, one road, and so on. Right. So from there, being able to have descriptions that look like this, a group of young people playing a game of frisbee, a car is parked in the middle of nowhere, sort of talking about these abstract concepts, it was quite exciting. What these models look like is what you would guess from what was going on at the time, that sort of using models that were popular for language, that were popular for images, and putting them together in meaningful ways so that we can have this image captioning system. So we're plugging in an image representation into the first state of the LSTM, and then that's producing a description going forward. And then obviously there were a whole bunch of improvements on the model architecture, various deeper models, wider models, various forms of attention, and things of that sort. And so, but right around this time, so once the excitement died down and people started taking a closer look at these models and what is happening, I think the community started questioning that when we think of image captioning as a way of demonstrating image understanding, is that what's really happening, right? And so, for example, at the time we could take this image and a model would describe it as a giraffe is standing in grass next to a tree, and many of us, including myself, would be quite impressed, right? That, oh wow, it's recognizing all these objects, it's figuring out what the connections are, it's describing it in natural language. That's great. But then if you look at just sort of random images from the COCO data set that have a giraffe in it, you realize that many of them can be described as a giraffe is standing in grass next to a tree. And so that's when sort of the community started questioning that, how do we know that these models are actually grounded in the image? And it's not, and maybe all that's happening is that it recognizes a giraffe and then everything else is just hallucinated. It just makes the rest of the description up. And so as we sort of probed at these models, we realized that that seems to be quite a bit of what is going on. And so since then, the community has worked quite a bit on trying to get these descriptions to be more grounded in images. And so here's one example piece of work. This is something that I was involved in, so it's a biased representation, but that tries to do this. So at the top, what you see is the Baby Talk approach, where I described it to you earlier, where you use these object detectors, you have a templated description, and you're just slotting in the various objects. So this is a photograph of one blank and one blank, and then you continue from there, and the model is just plugging in what these blanks should be. And so what was nice about these approaches was that, so the downside was they weren't natural sounding, but what was nice was that they were very much grounded in what you can see in the image, right? Because there it was explicit slot filling. And so the only thing you would talk about is whatever the model saw in the image. At the other end of the spectrum is what you see at the bottom, these neural approaches that I described already, where it's sort of these end-to-end models, it's spitting out this natural description. It sounds much more natural, but we were finding that they weren't sufficiently grounded in the image content. And so what we had proposed, this was in 2018, was this approach called Neural Baby Talk, paying homage to the original Baby Talk paper, where the idea was that the neural network will first generate a template of what it wants the description to sound like. And then we plug in the different entities, the different objects that an object detector found in the image into those slots in the template. And so to us, it seemed like it was a sweet spot where the model is forced to be grounded. It can't talk about things that it's not seeing in the image. And at the same time, the template is being generated by the model. And so there is scope for the description to be more natural than what just a sort of a one fixed template would have done. Another attempt at trying to get these models to really be grounded in the image was this work on visual question answering, where the idea was that if we ask these models very specific questions about all sorts of details about the image, and if these models are able to answer those questions, then maybe that's a way of demonstrating that they do understand the image to some extent. What we found at the time was that we were a little too optimistic about that. We found that even in this question answering setting, there were a lot of biases that these models could pick up on from the questions. So for example, most questions that started with how many had the answer 2. And so if a model just guesses 2 without even looking at the image, it could do reasonably well for the counting questions. And so we had pushed on this more to have this balanced VQA data set, where for each question, we had 2 images that looked fairly similar, but had different answers to the same question. Again, with the idea being that the model would have to look at the image to be able to answer the question accurately. And we also had this set up for these more abstract scenes where you have very fine-grained control over what the content can look like. So you can make subtle changes to the image and the answer will change. And so the model really has to understand those subtleties. The VQA models at the time looked similar to captioning, what you would expect, using sort of components that were working well for vision and language and putting them together. And so here we are in 2021, our first VQA paper that I described was in 2015. We've been organizing these challenges every year, and you're seeing the performance of the data set over time. And I find this amazing. I mean, one, the numbers are going up, and depending on where your motivations come from, you might find that exciting. But if you actually play with these models, there are online demos for these different models. And if you interact with them, there's just such a stark contrast between what we could do in 2015, 2016, and what these models can do today. And so, yeah, and so that's where things stand for VQA. So this is sort of mostly what I want to talk about in terms of the trajectory, and now I'll sort of switch a little bit more to forward-looking, current work and forward-looking. So a lot of this progress that I described, in this case, I showed VQA, but you could make similar charts for a variety of different tasks in vision and language. And a lot of this progress was very exciting, was very exciting, but it was happening in a very task and data set specific way. So for example, when we wanted visual question answering capabilities, we went out and collected this large data set with images, questions, and associated answers. We thought of model architectures that make sense for this task. You train these models on this data, you evaluate on the data set, and that's how you kind of make progress. And then if you want to do image captioning, you do the same thing. You collect a data set for image captioning, train models specifically for that, evaluate, same thing for a variety of these different vision and language tasks that I was showing you. And this was fine for the time when things were sort of still in their early stages. But if you think about it, given where we are now, this is not very satisfying. One, because it seems odd that the visual linguistic representations would need to be learned in a very task-specific way. You would think that the connection between images and language would be somewhat generic, that you can use across a variety of tasks. And the other was also that it could result in things of this sort, where for this image, if you ask the VQA model, what is the man making? The answer might be cake. But then if you ask a captioning model to describe the image, it might say an older man is wearing an apron and making pizza. And so these models are inconsistent. And so that's not ideal either. And so what we were interested in doing was to see if we can have a common model that learns sort of the basic representations of visual grounding, that learns these common visual linguistic representations that we can then use for a variety of downstream tasks, right? And so this was sort of the motivation behind Wilbert, and there were many other papers at the time with similar ideas that all came out around the same time. And the idea was kind of something that was happening in vision already, right? Where you would pre-train these visual representations and then you fine-tune for a variety of downstream tasks. And right around this time, we were starting to see signs of that for natural language processing as well, with models like BERT. And so that's, so actually a quick question, given the technical difficulties, I lost track of time a little bit. Can someone let me know how much more time I have so I can pace myself?
Yeah. So given that you have 5 more minutes, I would say, given the delay that we had.
Okay, that sounds good. So, that sounds good. I will try and wrap up in 5 minutes. Right. Yeah, and so that's what we did, where you can learn these common set of representations and then fine tune for a variety of tasks. But that was still a little bit non-ideal in that you still end up with task-specific models because you're fine-tuning for each task. And so what we tried after that was to see, can we have one model that has a large sort of a backbone that is shared across many of these tasks, and you have these very shallow heads that are task-specific. And so that way you have one model where for the same model, you give it an image and a question, it will answer the question. For the same model, you give it an image and a caption, it will score how similar they are. You give it an image and a phrase, and it will draw a box around where that phrase is in the image. And so that to me was quite exciting, when we had this one model that can do a variety of these tasks. You're welcome to check out the demo online. It's called wilbert.cloudcv.org. I won't walk through that right now, but it's, yeah, it kind of gives you a sense for what these models can and cannot do right now. All right. And so what's next? I think in this direction, sort of, we are moving in this direction of having sort of a clean, unified, effective transformer architecture for sort of that can, where the model can do not just vision and language tasks, but also vision tasks alone, language tasks alone, and sort of moving closer to having these generic models is, I think, what's exciting. This framework, it's called MMF, stands for a multimodal framework, is something that Facebook AI Research has open sourced. And so if you're interested in this space and trying any of these models out, doing your own research in this space, this can be a good starting point. So you're welcome to check that out. Let me just comment on, actually, maybe I shouldn't do this, because this is probably the elephant in the room, so to speak. So one thing that comes up when you talk about vision and language now is that, like, why has OpenAI's CLIP not just solved the problem, right? Why is that not the end of everything? And so I think CLIP is a very powerful model. For those of you who may not have been following it along, it takes as input image and text, and it can sort of align those. It can give you a retrieval score for how good that matches. And so it has demonstrated a lot of effective things for example, for better vision models, where you can just train these classifiers with no examples. You can just give it a phrase, and you already have a classifier that can recognize it in many different images. But I think we are yet to see its effectiveness being demonstrated in a variety of these different multimodal tasks, including generation like image captioning or VQA and things of that sort. The community is, I think, actively working on that. I've seen several papers that try to do that, but I think that is yet to be seen, and I think there's a lot of exciting work to do here. Some other challenges I think that perhaps don't get quite as much attention, but I think are important is, one is this ability to read and reason about text and images. I had mentioned visually impaired users as aiding visually impaired users as a motivating application here. And one thing that we found, so there is a VisWis data set that has data from visually impaired users. And one thing that we found there was that a lot of the questions that users have is about various text that is written at various places. And so reading and reasoning about that is important, and I think is still not close to being solved. Another, and perhaps close to the hearts of many of you here at this conference, is incorporating external knowledge. If the question is which liquid here comes from a citrus fruit, just the image on its own might not have enough information to answer that. You might need to leverage external sources of knowledge, and figuring out how we can incorporate that effectively, I think, is an open problem. And finally, a lot of what I talked about was for static images. All of this is sort of much harder for video, and videos are also just sort of computationally more expensive to work with. And so in general, a smaller percentage of the community tends to work on it. And so I think there's a wide set of questions that remain open for vision and language in the context of video. One meta point that I will make before, in this last 1 minute that I have, is that sort of when we look at vision and language in the past, we've sort of seen a lot of situations where in this space, we will leverage things that work well from computer vision, we will leverage things that work well from natural language processing, and see what we can do at the intersection. With things like OpenAI's Clip, for example, and other efforts like that, we're starting to see how vision and language is now also sort of giving back in the sense of improving visual representation. So you can do things in vision that you couldn't before this. And I think this link, I am yet to see a lot of convincing evidence for. I've seen pockets of it, but I haven't quite seen as much of sort of ways of using multimodal data to really sort of improve language understanding in a meaningful way. And so I think if we can do that, I think that would be quite exciting. And finally, I think generative models. That's something that I'm quite excited about, especially in the context of sort of creative expression. These are just some pictures that I by the handle that I've shown on the screen. And so I think thinking about multimodal generative models, if I give as input description, can we generate images that are faithful to that description? Can we generate videos that are faithful to that description? I think that's an exciting direction. And so to summarize in terms of what I think is exciting going forward, I think these more general models that can do sort of solve vision tasks, language tasks, and multimodal tasks, I think is exciting. I think right now there's just a lot of activity in vision and language. And so I think that is nice. There are many impactful applications that I mentioned. So if that's where your motivations lie, this could be of interest to you. And finally, things like incorporating external knowledge, looking at videos, looking at generative models, thinking about creative expression in this multimodal space. I think all of those are things that I'm excited about. And so with that, I will stop, and apologies again for the technical difficulties.
Okay, thank you. Definitely, you gave us a lot about. Actually, during the talk, the quality was fine. So yeah, you can turn back your video camera. We had many questions throughout. Maybe Samir will pop them. Yeah, cool. So I'll just jump right in because there's more questions than time. So the first question, do you think better vision understanding can, well, I guess you touched upon this, can lead to benefits in pure language understanding? In other words, do you think vision techniques will lead to grounded language models?
I touched on this towards the end, and I do think that there is a lot of potential here. I think, like I was saying, I think I haven't seen, so conceptually it makes sense to me. I think in practice, I am yet to see convincing evidence of that. And so I don't have a very good handle on why we haven't seen this yet, but I do think there's a lot of potential for this.
Yeah. I think I saw one paper from Mohit Bansal on Vocans or something that was related. That seemed very interesting.
Yeah.
Okay. So multitask transformers are quite powerful and impressive. However, they are hard to interpret or understand. What do you think are ways to balance the both?
So I think I have mixed feelings on this, to be honest. I think one is, it's not clear to me that they're a whole lot less interpretable than what sort of these deep ResNet models were before this that we were working with. So yeah, I feel like I don't think there's a qualitative difference in how less interpretable they are. And second, I think when we think about sort of interpretability and thinking about explainability and all of that, I think it's important to ground those in what it is that we want to do with that interpretability. Is it so that we're trying to sort of probe at the biases of what these models have learned? Is it that we expect a human to be in the loop that are using these models, and so they want some transparency in what the model is looking at so that they can make better decisions? And I think depending on what this motivation is and what is the use case for which we want interpretability, it changes significantly how you think about it, how you think about evaluating it, how much it matters. And so I think, and there was this XAI program for 4 years that many different research organizations were involved in. And for a while, even at the end of 4 years, I think no one really figured out how to evaluate for this. And so I think these conversations need to be very contextualized in what it is that we want this interpretability for. So yeah.
Yes. Okay, so what do you think are the bottlenecks for the current vision language problems?
So I think there are several. I think one is what I was saying earlier, that language priors tend to take over very easily, and it's hard to get these models to stay grounded in the visual content. I think we've made significant progress in that direction, but that still continues to happen. Models will hallucinate things and so on. And so I think having those grounded, I think, is important. The things that I mentioned towards the end, looking at videos, looking at how to incorporate external knowledge, all of those remain completely open problems, and not a lot of attention has gone into those. So I think those still remain. And another is the dependence on data. That a lot of the progress that we've made has relied on using large quantities of data. And so when you have concepts and entities that are not well represented in the head of this distribution, these models don't work well for those at all. And so thinking about how we can get these models to work well, even if you don't have a ton of data, using just a few examples and things of that sort, I think that also remains open.
Okay, I think we have time for one more question. So there is a claim in the language community that you cannot learn the meaning of language from text alone. Do you think with images that would be enough?
No, I don't think so. I mean, I suspect that many other modalities are useful also, right? That like just from static image, like just watching static images or watching videos passively, I don't think will give us the full handle on language. I mean, it might be helpful, but it won't give us the full language. And so interacting with the world, touching things, manipulating things, all of that is likely helpful in terms of being able to get, in terms of being able to learn more from language. So no, I don't think vision alone would be enough.
Okay, so there are many questions that we did not get to. So I do hope you can join us at Gather in around 15 minutes for the very thought-provoking talk. So now what we will have, Samir, if I'm not wrong, is with spotlight presentations for 5 papers that will later be presented at the poster session. So, and then 15 minutes after that, like in 15 minutes from now, I think, let me just check, like in 10 to 15 minutes from now, we will all go to the chats and poster rooms for chats with Devi and Yolanda, and for the poster session. So Samir, whenever
This
you're ready.
video presents our work on scientific language models for biomedical knowledge-based completion. There are many important tasks in the biomedical domain that involve identifying relationships between entities, such as repurposing drugs to treat diseases, or identifying diseases that are related to a particular gene or protein. These tasks can be framed as predicting missing links in a knowledge graph. While existing work has explored the use of large pre-trained language models for knowledge graph completion in the general domain, we are the first to systematically explore their use in the biomedical domain with comparisons to existing knowledge graph embedding methods. To perform our study, we used 3 biomedical knowledge graphs centered around drug discovery of varying sizes and types of entities, and collect names and descriptions for all entities from online ontologies. For these datasets, we find that language models and knowledge graph embeddings each perform well on different subsets of examples. Motivated by this, we explore methods of integrating language models and knowledge graph embeddings to leverage their complementary strengths, applying both previously used weighted averaging of their outputs, as well as training a classifier as a router to predict which model will perform best using features of each example. We find that model combinations that include a language model often outperform ones that don't, and that the router can do better than weighted averaging on several datasets. Finally, we find that language models can perform well in the inductive setting and can be used to fill in knowledge graph embeddings of unseen entities in order to improve their performance as well, an important feature in the rapidly evolving biomedical domain. To encourage further work on this task, we make our code and datasets publicly available at this GitHub link.
As a short introduction of the paper, do boat and ocean suggest beach? Dialogue summarization with external knowledge. We humans can infer meanings from the situational context even though the meaning is not literally expressed. For example, in the below dialogues, when people talk about ocean and abandoned boat, we can't think of beach easily because that's what ocean and abandoned boat tend to co-occur. Neural summarization models should also have such inference capability. We construct the dataset of our experiments using dialogues from vStyle and the corresponding image captions from the MS COCO dataset. The captions are used as summaries for those dialogues. We also define a novel term here as concepts out of the dialogue context, which is CODC. It's defined as the concepts that have appeared in the summaries while not appeared in the dialogues. We would like to focus on them explicitly during inference. Here is the overall model framework. Firstly, we have a knowledge retrieval model using features like word-to-vec similarity, word-net relatedness, and co-occurrence features. The retrieved knowledge are then fed into the encoder-decoder framework via a knowledge attention module to generate final summaries. The proposed model can outperform baselines in terms of both conventional metrics and newly developed metrics regarding CODC inference, which are precision, recall, and F1 regarding CODC. The experiment shows that such out-of-context inference module is indeed required for such dialogue summarization tasks where out-of-context inference are needed.
This paper is really about analyzing to what extent we can use entity embeddings for reasoning. Now, as a motivating example, we can think of inductive knowledge graph completion. So the idea is that we have a pre-trained knowledge graph embedding that has representation for entities like wings, feathers, and flying, and a pre-trained representation for relations like has, part, and capable of. And now we have a new entity, and all we know for that entity is that it has wings, it has feathers, and it's capable of flying. So basically what is happening in inductive knowledge graph completion is that we're using the available knowledge about E to learn a vector representation of E, and from that vector representation we can then predict further plausible knowledge. So essentially these triples that E is involved in, we can think of them as attributes because the only unknown here is the entity E. And so the framework that we're looking at is really where we have some kind of vector representation of these attributes that we have about entity E, which are used to construct a representation of E as a vector. So somehow we're pulling attribute vectors. And then we have some kind of scoring function, which we can think of as a decoder that allows us to predict missing attributes. Now, we say that this framework models a rule like has wings and has feathers and can fly implies is bird, if it is such that whenever the attributes has wings, has feathers, and can fly are initially given, the representation of the entity that we're learning is such that we would predict the attribute is bird to hold as well. The main result in the paper is to analyze for different combination of pooling strategies and different labeling functions, what kind of reasoning can be simulated. So is it in principle possible to simulate the rules that are entailed by a given propositional knowledge base? So that's what you can see in the column about monotonic reasoning. And then we do the same analysis for a particular framework of non-monotonic reasoning.
Hi, I'm Jinhyuk Lee from Princeton University, and I'm going to present our paper called Phrase Retrieval Learns Passage Retrieval 2. This is a joint work with Alex Vetic and Danchi Chen. Our work builds on a paradigm called phrase retrieval for open domain QA. Here, phrases are any contiguous segment of text up to L words. In phrase retrieval, one of the 60 billion phrases in Wikipedia is retrieved based on the maximum inner product search with the question vector. Dense phrases is a phrase retrieval model that uses dense representation of phrases and questions, which achieves very strong performance while making the inference much faster and simpler. We motivate our research from the observation that many retrieval methods have fixed granularity of text to retrieve. For instance, we might need to encode a sentence for sentence retrieval and a passage for passage retrieval whose definition can change in different models. But do we really need different methods for different granularities? In this work, we use phrases as a basic retrieval unit for multi-granularity retrieval, since retrieval of phrases entails retrieval of any larger granularities, while the opposite direction doesn't really hold. With dense phrases as a phrase retrieval model, you can retrieve phrases as well as sentences, passages, and documents. Without any retraining, We find that dense phrases easily outperforms existing passage retrievals on passage retrieval tasks, and we further show that it also works well for document retrieval tasks. We also investigate why it works so well and find out phrase retrieval naturally differentiates hard negatives better. We also include details on how to reduce the size of 300 gigabyte phrase index down to 20 gigabyte with minimal performance decrease. You can check out our paper and code for more details. Thank you.
Hi, this is Satoshi Sekine. I'm going to talk about Synla 2020 ML task and resource. The goal of Synla project is knowledge-based construction for explainable AI. What do we do is categorizing and structuring Wikipedia. And how we do is to run the shared tasks to build a resource together. Okay, and among the 6 tasks we have been doing, Synla 2020 ML multilingual task is to categorize 30 language Wikipedia pages into 200 extended name entity categories, which is find, brand, and need. And this is extended name entity. For example, name has a product, product has a vehicle, vehicle has a car, train, aircraft, etc. And the final goal of Synla is to create a well-structured knowledge graph like this. And we believe the existing knowledge base and knowledge graphs are very noisy. So that's why we are doing this. Okay, Synla 2020 ML task is a shared task to build resource together. We prepare the training data, test data as usual, but we don't make the test data open so that the participants have to run the system for the entire Wikipedia. And the system outputs are open to public and anyone can do anything, including ensemble learning. And it run on in 2020, 2020. And as again, the focus is resource construction, not evaluation. We call it resource by collaborative contribution. And we got about 10 participants from many countries. And this is a evaluation results. The best system performs something between 80 to 85, and one system dominates in many languages. But good news is a simple voting system, majority voting outperforms the best single system in most of the more than half of the languages. So that's good news. Okay, and this is a link to the project. Okay, so thank you very much.
I am Vaibhav. I'll be presenting regex queries over incomplete knowledge bases. This is joint work with Parth, Shrikanta and Mosam at Indian Institute of Technology, Delhi. Currently, there are 3 types of queries which have been explored over incomplete knowledge bases. These are single hop, multi-hop and first order logic queries. However, in our analysis of real-world queries to Wikidata, we found that almost 12% queries are specified using regex operators such as clean plus and disjunction. To explore the problem, we constructed 2 datasets. Wiki100 is constructed from actual user queries, whereas FV15K regex has a larger variety of query types. We propose a new model for the task, Rotaty box. Rotaty has been shown to model a large number of relation patterns. On the other hand, box embeddings help in modeling large set of entities, a trait present in most regex queries. We established baselines for the newly introduced regex operators. For Clean Plus, we consider projection, which is trainable matrices as operators, and free parameter, in which every relation has a separate Clean Plus embedding. For disjunction, we experiment with aggregation and deep sets, which is a framework to learn permutation invariant functions. We find that on both datasets, regex variants of Rotaty box perform much better than all other methods, indicating that Rotaty box serves as a good base model for this task. Dealing with regex operators gives rise to novel modeling challenges, which are currently not addressed by our baseline models. In particular, modeling Clean Plus involves learning a parametric learnable operator which honors Clean Plus properties such as idempotent unary operator as well as infinite union of path queries. We hope this work will encourage further research in this area. Thank you.
Okay, hi everyone. So the last part of today, we will now have in parallel both a 30-minute chat with our speakers, Yolanda and Devi, in the chats and poster room. And in parallel, we will have the poster session for the next 90 minutes. And that will be it for today. Please join us tomorrow in the main hall for the outstanding paper session. See you soon.